in the heart. They look like they're this big, the entire pacemaker, and they're attached into the ventricle, and that's the entire pacing system, which, while it's possible that these devices may not be detected, at the same time, to my knowledge, these devices also have MR conditional labeling, so we wouldn't have any need to detect them in a sense, but you should at least be aware that there are other pacing systems out there that are leadless and therefore have a different environment for us to consider. We were talking about radio frequency burns, and we said that in a sense you had to think like an electron as to where the oscillating magnetic field that you irradiate the patient with, where would the induced electrical fields cause an electron to wish to flow, as it were, as it creates its own circuit. So think of path of least resistance, and I think you'll be in good shape. But one of the most important things I wanted to point out to you is that we may irradiate here, and therefore, of course, it goes without saying that whatever area you irradiate with an oscillating magnetic field may therefore have the potential to have induced electrical voltage that could, if there's a high resistance part or a large loop or whatever, it might be possible to cause a burn in that volume directly undergoing radio frequency irradiation. But at the same time, it's also possible that irradiating in one location may induce voltages, which induce currents, which can cause electrons to flow in regions that are not within the volume that underwent direct radio frequency irradiation. So you may scan in one location and get a burn in another. And this is most likely, in my opinion, to happen if you put in to that patient a superhighway. And for an electron, what would constitute a superhighway? A wire, right? A lead. An electron looks at the lead and it says, compared to anything else I see in front of me inside this human, that piece of metal is going to be a lower resistance pathway for me than this muscle, than fat for sure, than skin, than liver. I'm going that way. And so if there's a wire or a lead, you can pretty much rest assured you're going to be inducing currents inside that wire or lead in magnetic resonance. And if that wire or lead is even partially within the region that is undergoing direct radio frequency irradiation, be really careful where the other side of that is. So a hunter wanted to have an MRI examination. I don't know if that was his job or his hobby, but he was a hunter, and it's an integral part of this issue. He needed to have direct bilateral simultaneous depth electrodes into his thalami placed. And essentially the depth electrode, it's a pacemaker of the heart, of the brain instead of the heart. It doesn't pace it the same way, but it's got a pulse generator, it's got a power supply, and it's got a lead to deposit that electrical pulse somewhere. Instead of the heart, you're dumping that energy into the brain on a regular pulse basis. Got it? So it's essentially a pacemaker. You just put it somewhere outside of the heart. And they do miracles with some of these things today in the brain, which means just expect to see more and more and more and more and more and more and more of them as the years pass. Having said that, he was a hunter, as I told you, and he had to have bilateral implantation, so they typically implanted subcutaneous on your larger versus smaller patients. They don't dig. They just plant it right under the skin, subcutaneous pocket. And he said, you know what? He was a lefty, I believe, because he said, on my left side, I don't want you to put the the box. Don't put the can over here, because it may interfere with my weapon. Can you put it somewhere else? And they said, sure. So they tunneled down to the epigastric area. They do that for kids as well. They just put it in the subcutaneous tissue down here, and they let it tunnel into the brain on both sides into the thalami. This guy goes, gets his depth electrodes, and he goes and minds his own business. A few, I don't know, months or years later, he gets low back pain, doesn't everybody? And he goes to get an MRI of his lumbar spine, 1.0 Tesla lumbar spine MRI, and he blows a 2-centimeter hole in his brain, only on the left thalamus. He blows a 2-centimeter hemorrhage intracranially on the side that was partially irradiated, even though that energy got funneled and deposited and concentrated. Physicists hate when I use the word focused. I actually couldn't care less. That's how I think of it. It's focused, it's concentrated. It was concentrated right there. Interesting bit of trivia, it's not the tip that heats up at all. It's the microns away, it's the right past the tip where the E fields concentrate in the tissue. That's where the burn is likely to occur, and that's what happened with this gentleman as well. So I'm just trying to make sure that you understand that in a sense you have to think like an electron. You irradiate certain areas, and that causes energy, force. That force, E fields, electric fields, are going to want to generate forces, a voltage. A voltage is a push. And it's going to try to push your electron. In order to know where that push is going to go, think like an electron, think like a male. Path of least resistance. And that's what it's going to follow. And see if you can use, if you see large loops, watch out for areas of small surface area. It's a nice thick pathway for the electrons to go here. If anything, you know, if you have 10-lane highway and then all of a sudden they're doing construction, it's right where it goes down to 2 or 1 lane. That's where the greatest friction is. That's exactly what's going to happen. The greatest resistance will be if you have a path of least resistance that meets a lot of resistance. They tell you never let large loops being formed in MR. I think that's great advice. But I don't think I've ever in my life heard anybody have any kind of radio frequency issue going into an MR scanner like this. First of all, you can't. The darn thing's too tight. But even if you could do this, I'm not advising that you should. Flashlight number 3, neurostimulation, that's another story. But when it comes to flashlight 2, the radio frequency issues, I don't know anyone who's ever even come close to reporting any injury from this. But you know what you do get injuries from? This. And you can see it, right? Right there. It's where the surface area for that path, where it's going to be a very small, narrow area where the resistance might increase, and that's where you might have concerns about burns. Burns is a massive issue. It's literally hours and hours and hours. I maintain that there are multiple different types of burns, different etiologies to burns in MR. We're not going to cover them all today. I just wanted to give you some exposure to the concept of another energy, another flashlight, another type of risk, in this case thermal. The B1 maps of an unloaded transmitting radio frequency coil do not tell you where the burn occurs. That comes from your brain, unless you have some physicist and all the simulation software in the world to try to figure out where the E fields will be, which you don't, nobody does. That has to be done on a case-by-case basis. You're just looking at where the magnetic exposure, the transmitted oscillating magnetic fields are going to be. We have to use our brains to try to predict, is there anything in there that might cause a burn? Or is it potentially going to lead that electrical voltage, is it going to lead to a current outside of the volume that will be irradiated and cause a burn somewhere else, perhaps? And so B1 maps help you as long as you recognize they don't solve for you. They give you an idea of where the power is being transmitted, but not where the burn potential will be. I'm going to show you MagnetVision in the app in a moment. It's important that you recognize that that will show you the B1 magnetic fields. It'll show you what are you irradiating. It makes no pretenses of trying to show you where an induced voltage will be and where induced currents might flow. So, in order to know where that would be, for some of these types of burns, I think it's important that you think like an electron, so to speak, and keep in mind, whatever you're irradiating, is there a low resistance pathway in there? Whether it stays in there or goes out of there, is there a low resistance pathway there that it would want to follow? And is there, in that pathway, is there one part that may have high resistance? That's where you have to worry about potential burns, at least of one type. And remember that that pathway may extend outside of the irradiated volume. This is that Hunter I was telling you about, a Parkinson's patient. This is where he had his electrodes, and that's where he blew a hole on that left side where it was actually planted in the epigastric area. And this is the FDA report. I should point out the report to the MedWatch database was 1 Tesla. They showed you where it was. The part I want you to see is the manufacturers. The manufacturer instructed the healthcare practitioner that full body coil MRI is not to be used on patients with manufacturer's implantable devices due to heating and electrical conduction during MRI. The healthcare practitioner proceeded with the MRI scan. Can you see them like hanging you out to dry? You did the mistake. You're going to pay for it. They're certainly not going to share in that one. RF thermal issues have occurred when you have wires or leads or devices or metallic electrically conductive material in there, but it doesn't have to be. Yes, it can certainly be that you have a reflective aluminized backing to some kind of nicotine patch or medicine delivery patch. Sure, it's even happened with electrically conductive eye makeup, tattoos. But it can happen with tissue without having anything external. If you yourself, your own tissues, form large loops, that can itself be sufficient to cause a burn in magnetic resonance. This is a burn of a patient. These are all from legal cases. This is a burn. Patient had massively developed medial calves. I take it back. I'm sorry. This one case is not a legal case. This one is from published literature in radiology by Dr. Michael Knapp, first author. A large loop, they were irradiating the thigh. He had massively hypertrophied calves. And can you see this huge loop right here? His medial thighs were not touching. His calves were touching. RF coil, the body irradiating right over here. Probably the largest loop a human can form other than trying to touch your toes in the magnet. And with a very large loop, he developed kissing third-degree burns. This is months later. These third-degree burns were present on this patient. Dr. Yamazaki showed that it's because of induced voltages. This has electrical conductivity similar to human tissue. And if you, this is the theorized, the legs. This would be the crotch. This would be the thighs. This would be the legs. Can you picture the phantom? And so he said if you have them space apart a centimeter and you expose them to MRI, no heating. This is temperature, no heating, despite letting them scan for almost an hour. Now do the same thing where you're touching them, but artificially, the gradients are doing their things, flashlight number 3, I guess, but the RF, turn it off, don't let it work. So you're artificially not using one of your 3 flashlights. No heating. And then he turned off the gradient flashlight and said no gradients, but do the same study this time where the RF is transmitting like a normal study, and now you can see the heating because of that large loop with high resistance, and those are the places, as you might expect, high resistance, that's where the burns might occur. This patient was lying like this. Can you see me from the back? He was just lying in the magnet like that, and he's lying in the back. He got a burn, hypothenar to his thigh, just from the large loop. And that's why they always tell you pads, ladies and gentlemen, pads. People say that we've got cases reported to the FDA. They testify against themselves. They say, I was certain to use a sheet between the patient and the magnet wall. It's another type of burn. They want these to be non-electrically conductive loops. So the pads are there to give you distance and to give you resistance. And listen to them. They know what they're saying. Use the pads. Dr. Schaefer's did this simulation of E fields. This is not the transmitted energies. This is the induced voltages. And this would be the head and neck and the chest. And this would be the crotch. And these would be the thighs. And I think you can see that there's a hot spot that they theorize between the contact of the thighs. If you don't put a towel or a block or something between a pad. This is from a lawsuit, exactly where this patient had his burn. Another patient, exactly where the medial thighs, third-degree burns. Think like an electron. Slide courtesy of Dr. Claire Timpany, a burn from lying on an EKG lead, a second-degree burn. Tattoos can burn. Clothing that's electrically conductive is now in use everywhere, especially sports clothing. This is an article published showing electrically conductive undershirt that this person wore and got second-degree burns. In this example from carpal tunnel, ironically, the patient's ID band was electrically conductive, resulting in a second-degree burn. But the second-degree burn here, those of you that have any experience in the wars or what have you, second-degree burn here, what happens in the legs, what happens in the arm, compartment syndrome, it starts to swell. The compartment's sealed. The compartments are very, very tight areas. You put in fluid and it swells. What happens? The pressure increases to the point where it exceeds mean arterial pressure and you cannot perfuse and you lose the limb. Guy goes to a war, he gets a tiny little shrapnel injury in his calf. He figures he'll run through it. Next thing you know, 2 days later, they amputate his leg because it's swelled up, the pressure increases from a tiny little injury, compartment syndrome. So because he started to develop compartment syndrome, he required decompression and eventually allowing him to heal back. All this from an MRI examination. So I showed you the spatial plots. Where are these energies for the static field? Where are these energies from the dBdx, the magnetic spatial gradient? Now we have another flashlight, radio frequency oscillating B1 fields, right? Where are the RF energies being transmitted? I don't know. Which manufacturer are you using? Which coil? Which transmitting coil? Stop telling me about the receiver coils. From a point of view of burns, nobody cares. The only thing I want to know is which one is the one that's going to transmit these potentially harmful energies into this patient. The receiver coil is, stay with me here, receiving, hence the name. We're worrying about the transmitting coil. That's the one. In the United States, the vast, vast majority of my physicians would not know which coil you're using for RF transmission until you tell me. Are you using a body coil? Are you using a head coil or an extremity coil? Does your machine even have any other coil to transmit other than the body coil? Some manufacturers will 100% of the time transmit with the body coil. That big thing that's inside the magnet, you never get to see it. It's behind the faceplate. What are the dimensions of your body coil? If you're scanning the head, does it irradiate the guy's vagal nerve stimulator? Do you understand the questions I'm asking? If you don't know, who's going to answer? Certainly my radiologists don't know the answer to these questions. I'm going to turn to you. I'm going to ask the radiographer to answer that questions for me. Because today, in the old days, it was hard to get any of this information. Today, all the manufacturers provide the information to us. And they'll provide you these kinds of plots. And they'll show you this is a log scale, this is a linear scale. But they'll show you this is the magnet. This is the center of the magnet. That's 1/2 of it. The patient would come in this way. And this is 1/10 the exposure. RF is that. This is 100. This is 1,000. Does that make sense? And this is distance. This is 1/2 meter. This is a meter. So for this older machine, which is quite a large machine, as you can see, a long bore, somebody standing, what mom wants to know, can she stand by the outside? The pregnant nurse practitioner, the nurse anesthetist standing at the front bagging a kid in the scan. Can she scan there? What am I being exposed to? If you can't answer that question, who is? Who is going to be able to? So here, standing at the surface at the front, she's got approximately 1/100% of the maximum exposure happening in the center of that bore when it comes to the RF flashlight. When it comes to RF energies that we're transmitting, it's about, in this example, 1/100%. In a different scanner, a shorter bore, it's about 2% of what's happening in the center. In a different scanner, once again, every RF coil is unique to that coil. What is its transmitting profile? If the inferior end of the body coil goes to there on this magnet, then if you go down 55 centimeters for the body coil, let's say in this example from here to here, then about 15 centimeters below that, it's about 10% the exposure. So if there's an implant that's about 15 centimeters below the lower end of your body coil, but you need to know where the body coil is going from where to where, and when you position that patient for this study on that magnet, where will that implant, remember that star on L4, where is it going to be? If it's going to be down here, it's about 3%, not 10% of the exposure max in the center of that coil. If it's down here, if it's down at the outermost part, sorry, I have to run through the whole thing again. 10% here, 30 centimeters below, it's about 3%, and 45 centimeters below, it's about 1% of what's happening in the center. Does everyone understand that? So you need to know when you stand in the back of the room and turn on a flashlight, where is the implant in this room? How much energy is it being exposed to? Your room is your patient. Another manufacturer and how they depict RF energies, One end of the coil, the other end of the coil. This is isocenter, is right in the middle. Energies from the body coil transmitting as you go into the center and out the other end. Does everyone understand what this is showing? These are spatial distribution maps of the RF transmitted energies, just like we showed maps of B0 and we showed maps of dB/dx. Now you can get maps of the RF energies. And then the gradient one. The gradient energies are not that efficient at inducing heating. They can induce noise, the banging, the buzzing, that comes from the gradients. They can induce electrical excitation, that's going to be our number one. The biggest concern here is peripheral nerve stimulation, causing an action potential for a nerve. A nerve just sits there minding its own business. That means a nerve which can conduct electrical energy will do nothing until you add voltage to it, nothing happens. You add more voltage, nothing happens. You add more voltage, nothing happens. When you get to a certain level, bang, it discharges, and it sends a signal down the nerve. There's no such thing as a partial. You are never partially pregnant. It's quantum. Quantum means all or none. You are or are not pregnant. The switch is either on or off. As opposed to analog, you may have a rheostat, right? It could be brighter and brighter and brighter, darker, darker, and it changes. Quantum means all or none. An action potential did or did not discharge for this nerve. There's no halfway. You either reach a discharge threshold of voltage, at that voltage or above, bang, that nerve will discharge, and whatever it's connected to on the other end is about to get stimulated. If it didn't reach that action potential level, if it didn't reach that discharge threshold, there will be no signal and it will not stimulate whatever is on the other end. It's as simple as that, all or none. The stimulation of that nerve can occur because of a gradient. I want to make sure you understand this. That means you're going to be imaging. The first flashlight, the first energy source is a strong magnetic field and its distribution in space. The second energy source is radio frequency oscillating magnetic fields that you will shine, irradiate parts, but not all, of that patient with. The third energy source is a coil, technically left, right, front, back, up, down, 3 sets of coils all centered to the same position in space. And you're going to turn them on, off, on, off, on, off, on, off, thousands, tens of thousands of times per second to generate an image. Turning those on and off can be done so quickly that you can take a nerve in a human body, bang, cause it to discharge and send a signal. You can cause direct neuromuscular stimulation, excitation of a human by an imaging procedure. We weren't doing this before. This is new for us. So they regulate this too. And they regulate it statistically because different humans have some ranges as to what will cause that discharge. Furthermore, listen to this. Different nerves in the human body are more or less sensitive to reaching an action potential. This much voltage will blow those 7 nerves right there. Bang, they're going to discharge an AP, an action potential. These 14 nerves are just going to laugh at you. Oh, to get those, you need to go much higher voltage. Then, bang, they discharge. And luckily for us, one of the nerves that requires one of the highest voltages to get it to discharge is the one that controls the heart. Nobody cares about peripheral nerve stimulation. We can cause, by imaging, we can cause your muscles to twitch. This is not a joke. Direct neuromuscular excitation by MRI has been reported dozens and dozens of times. The imaging sequence results on, you're sitting there saying, what's going on? My nose is twitching. Yeah, your skin is contracting. It feels like ants crawling on the small of your back. Directly, the imaging is causing the muscles in the back of your largest radius, largest induced voltage, and all of a sudden it starts to twitch. It's like ants crawling on me is what they've reported. That's called peripheral nerve stimulation, and we regulate PNS levels. PNS levels are regulated. Don't look at me like that. I didn't say it. You thought it. But we don't care about PNS levels. In fact, by the FDA, in case it's of interest to you, FDA has a category called significant increased risk. You can continue with gradient changing and how high a voltage you can induce. It's not considered an increased significant risk until you reach pain tolerance. You could twitch that patient right off that magnet. If he doesn't say, ouch, it's not considered a significant increased risk by the FDA. What is considered a risk, and what we're actually trying to regulate for, cardiac stimulation. That we would not want. Cardiac stimulation, we give another word to, we call that an arrhythmia. So arrhythmogenesis, inducing an arrhythmia, is what we're actually attempting to avoid. And thresholds are meant to regulate the chances of causing peripheral nerve stimulation. Because if you didn't cause PNS, you're not going to cause cardiac stimulation. And so you will find regulation here to regulate that we do not have, or that this is the chance of causing peripheral nerve stimulation. Normal operating mode, 80% of the population. Half the population might have some reports of neuromuscular twitching. If you go to first level controlled mode, it's too much detail for today. But what are we regulating? Peripheral nerve stimulation. Because if you're not reaching that, you're not going to excite the heart and cause an arrhythmia. Everything I just said falls into inconsequential consideration if you put a superhighway in that heart. Everything I just said and all these levels that we're allowed to use, yada, 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 becomes garbage. If you decided to give that male electron a superhighway and an easy path to follow and put the other end of that highway into the ventricle. So somebody that has a pacemaker, an implanted stimulator, a retained abandoned cardiac lead, if you are imaging any part of it, oh my God, stand up and take notice. There's some real potential danger here. Because now we're talking arrhythmogenesis potential. But in order to know, are you irradiating any part of it, don't tell me about the static field and stop talking to me about RF. Now we're talking about gradient stimulation. Where are your gradient energies? What's the size of your gradient coils? Left, right, front, back, up, down. Do you know? If you don't know, how do you know if you're irradiating that little star at L4, right? How do you know if you don't know where the energies are being deposited? So I'll show you. So conceptually, there are three different energies. And induced voltages is the biggest energy that we're worrying about with energy number 3, with the gradients, the imaging gradients. In this article by Dr. Ninehouse, probably one of the world's experts, if not the world's expert on this topic, a metallic implant that has conducting components will tend to concentrate the induced gradient currents. If there were a significant enough concentration, you can cause neurostimulation. It makes common sense. Can anybody tell what this is? I'm just curious. It's not an intelligence test, it's just a pattern recognition. This is half of a human in axial form. Imagine this is an axial view and you just mirror image this. This is the arm. This is the thorax. So from supra-inferior irradiation, this is the induced currents. Eddy currents. I have no idea why they call them eddy and not Scott, but they call them eddy currents. That was actually a joke. You can laugh at that one. But this is what you might expect to see them in the arm. Notice that the currents are greater with larger radii, larger diameter loops in this guy's thorax. This is the currents would look like, and obviously I think here you can tell what this is. This is looking at the guy from coronal and half of the patients there, and you can see where the anticipated pathways for the eddy currents would be in this. These are currents induced inside your human for every single study you do with them. And studies that, here it's the gradient, so the more rapidly you turn them on, off, on, off, on, off, that's when you get the greatest current density. And the ones that do that the most are the echoplanar sequences. Used to be called Instascan or Hyperscan, or now we just typically call them EPI or echoplanar. And which are the ones, anybody, blurt them out. What sequences, what names do you guys use? What sequences use echoplanar? Anybody? DWI, for sure. The angio sequences may be very high on your gradient DBDT. DBDT means a changing magnetic field per time, imaging gradients. DBDX or DBDZ was changing over space. These are turning on, off over time. DBDT, a changing field over time. That's the one that induces potentially direct neuromuscular excitation. And so anything that uses the perfusion sequences, The angio sequences will be high dBdTs as well. Certainly diffusion-weighted imaging. If you're doing an imaging sequence and it takes you a minute or less, you know you're using extremely rapid gradients, right? For most systems out there, you can't even control directly what that gradient dBdt will be. It's defaulted by the manufacturer. Some of the manufacturers now have, one of them is already out with it as product. You can say, do not exceed this amount of RF, do not exceed this amount of dBdt, and it won't. Others are going in that direction as well, which is good for us. But how do you even know if your implant is going to be exposed to this in the first place? You need to know the physical dimensions of your gradient coils. And where are they active relative to the implant? And remember that a gradient energy, well, I'll show you in a minute, the greatest change is where my hands are, not where my elbows are, and not where my shoulders are, right? So left to right, the greatest change is at the periphery. That way, anteroposteriorly, and don't forget, all important, SI. Because SI, I'm centered at the neck, but it's over here and over here, depending on exactly what the length of your gradient coil in your magnet would be. When you're scanning ahead, you're maxing the pacer. Just remember that. When you scan the pacemaker, one of you asked me a question during the break. What if you're scanning the pacemaker directly? What if you're doing a cardiac scan? Well, if you're doing a cardiac scan and you have somebody asked me that during the break, I have stents, electrically conductive stents in the heart. Can I use really, 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 really powerful gradients on them? Do you have any concern at all? So I'm not going to go through the whole answer, but one of the things I said was if you're scanning the heart, I'm least concerned about cardiac stimulation. Why? You're scanning the heart where the stents are, and that's your least concern. Why? Because the greatest changes are further away from the center, and right there, they're going to be towards the center of all three, anteroposterior, left, right, supra-inferior. That's where the changes are not so great. I'd be a lot happier if they'd be in the ankle. If you're scanning an ankle, my concern of you're having an abandoned lead may go to 0. An abandoned lead in your heart may go to 0 if I'm scanning your ankle. Do you understand? Now I need to know your body habitus, your height. I wasn't kidding about achondroplastic dwarf. If I'm scanning the ankle of an achondroplast, I may be exposing this abandoned lead to massive amounts of gradient. Do you understand? If it's a 7'3" basketball player or what, 2+ meters, and I'm doing a knee, do you really think I'm going to be worrying about that he's got some coils inside his brain and a vagal nerve stimulator and I'm down there? I can't even focus that far away at my age. There's no single answer. It's your patient. You need to know, where is the implant? Height. Weight. Why do you need to know weight? Body habitus. Is it going to be out by the periphery? Type of burn we haven't discussed, that if you're close to the periphery, very close to the periphery, you can be exposed to a different kind of a burn. Where is this relative to the bore, relative to the transmitted energies? Height, weight, we'll get to gender in a minute. What energy is it being exposed to? Are you doing a pit? Are you doing an ankle? Do you understand how all these make such massive differences? And the answer to the question, which is always, can I safely scan this patient with this implant? And just like we have plots for dBdt, just like we had plots for dx and for B0 and dBdx, we also have plots for dBdt. And this is one manufacturer's plot of the gradient coil. Remember, the gradient coils are epoxied into that MR scanner. You're not going to play with those for clinical systems. The left-right supra-inferior anteroposterior gradients are epoxied, bang, they're stuck in there. You don't even see them. And if this is isocenter, this is the gradient changing supra-inferiorly, and this is the start of the flare of this magnet. This is the edge of the board, just trying to give you an idea of what's happening where. A different magnet, different shape, a different magnet, different shape. Do you understand? I can't answer the question. The only one that can answer that is the radiographer. I like the name radiographer. I prefer the name technologist. It's got nothing to do with being American or not. Technologist means one who understands the technology. That's what you are. That's what we expect you to be. Now, with this in mind. So we have different energies. It's not just different energies. What we really have is we have different spatial distributions to these energies. I've tried to convince you that the different spatial distributions of these energies become crucial aspects to consider before you can determine whether or not you're going to scan a given patient. Let's change approach. We're going to change hardware. I think there's a lot here. I think there's a lot here. I need to know what hardware I'm using. I need to know where it's going to deposit what energy. I need to know what risk is associated with each of those energies. I need to know what implant or implants my patient has. I need to know the body habitus of this patient. I need to know where I'm centering. I need to know what position I'm going to place this patient in. And then I can start thinking about whether or not it's safe to accept this patient for that scan. I might accept him for the pituitary. I might not accept him for a knee, or vice versa. So one of the apps that we generated, which I'd like to use now under the guise of teaching you about the app, what I'm really going to do is use the app without your knowledge to teach you more of what we just covered. One of the apps that we developed was developed in conjunction with the MR manufacturers. We got together with them and we said, you know those maps that you've generated? I'd like more detailed information about them. And if you give me that information, I would like to translate them, if you'd excuse me, into English, or at least into some kind of a language that the people that really need this data would more understand. Tables depicting maximum spatial gradient of 840 Gauss per centimeter at a Z value of 134 centimeters from 0 have limited value to most of us, in my opinion. And what happens at 133 centimeters? So I would like different data from you that I would like to then present to the end users in a way that they can understand. So the one thing we do know is pictures. That we're good at. And radiologists, we're pattern recognizers. That's one of the things that we have as a tremendous strength. What's the strength of a radiographer? What is it that I would expect you to know? I've made two apps. The first one I call a checklist. I'm not even going over that with this group. We don't have time. But the checklist is really there for an MRMD, an MRSO, and even an MRSE. The checklist will ask you questions like, will the device or implant or foreign body be exposed to significant gradient dBdx, dBdt? And an average person who's never been exposed to this will look at that and say, what? It's meant for somebody with domain expertise. It's meant for people that have an understanding of MR safety. And so we wrote this for the rest of us. I'm not insulting us, God forbid. We have too much on our minds. We have too many things that we have to know, and we have to be better than anybody else in the hospital at them already. So what could I expect of my radiographers anywhere in the world? What do I expect? What would I demand of you? I demand you know the next patient. Who are they? I demand you know height, weight, and gender. I demand that you know what implants they have on or in them. I demand that you know where in that patient that implant is located. Are you listening so far? The second you disagree, you're too shy and you're way too polite to interrupt the speaker, God forbid. Can you imagine a classroom full of people like me? Would never interrupt you, Manny. Okay, I wish you would. But okay, so don't interrupt me. The second you disagree with any of these things, please just raise a hand, raise some appendage, and fling it around. I expect you to know the gender, height, weight of that patient. I expect you to know the implant or implants that that patient has. I expect you to know where in that patient, is it left-sided or is it right-sided? If that patient, listen to this, if that patient has a depth electrode in their left thalamus, I expect you to know that that can is epigastric and not in his upper chest. I don't expect that. I demand that. It's your job. I expect you to know which MR scanner you're going to place that patient in. I expect you to know how you're going to position that patient for the examination that I've asked you to do. Head first, feet first, decube, Superman, whatever I don't even know these things. You'll tell me. I expect you to know. I expect you to know how to center that patient. Oh, to do that, I would center at the canthal-meatal line, angled 15 degrees. No, the nipple line. No, for that, oh, no, no, no. I put my hands over here, and I put my finger back there on my thumb. That would be L4. I'd center that. I don't care. I expect you to tell me you know how to center that patient based on your external landmarks. Do you understand? If you don't disagree with any of the things I've said to you so far, we're done. MagnetVision is an app whose purpose is intended to take the expertise that you have and apply it so that I don't have to suddenly become, please forgive me, I don't have to suddenly become a physicist. And I don't ever want to see any of us pulling out calculators if we're standing and scanning MR patients. What I expect you to plug in is that which you already know and that which you are more expert than anybody else in the hospital at doing. So the program, the app is designed with respect to the physicist and with respect to the radiologist. The app is designed for radiographers. It's meant primarily to be used by a radiographer to produce a report that will be sent to the radiologist. And therefore, the app is designed conceptually into 4 rooms. The first room that you go into when you launch the app is a waiting room. And what would you expect to happen in a waiting room? Go get your patient. So in the waiting room, you will retrieve or you will define your next patient. Joe Smith, 192 centimeters and weighs 81 kilograms. Got it? Gender, height, weight. You can plug in everything else. You can plug in the ID numbers and everything else you needed for your medical records if you want to. Stop worrying about legal. Just worry about the physics. Gender, height, weight is the only thing the program needs for its calculations. Then there's an implant room. Think of it as a warehouse. In the implant room, the present iteration, which I'm hoping you will never use, the present iteration allows you to generate, it can create 3-dimensionally any implant you want, whether it exists or not. You want to generate a piece of shrapnel, put it any shape you want, you can. You want to generate a pacemaker, an implanted defibrillator, you can create anything you want to. Or you can just select it from a pre-existent list. Stay with me. So let's say you say, I'm going to pick that Blorg Model 300. Now you have an implant. The implant is defined, but ladies and gentlemen, this is not CT. When we define an implant, what does that mean? That means, I said, it's a Blorg Model 300. So the Blorg Model 300 has physical dimensions and size and shape and appearance to it, right? It's a wrench or whatever, right? What else does it have in MRI if it's going to be useful for me? It has labeling. So in the US, we use FDA. You use whatever your regulatory labeling is that you wish to use. And it's going to ask you, is this device labeled? And if the device is labeled, the labeling will be on the device. Or you can add your own. So for example, it's a Blorg Model 300 that's approved up to 3 Tesla, up to 540 Gauss per centimeter. Do you understand? So that's part of the identification of an implant when it comes to this program. What are its thresholds for safety? But Manny, I don't understand. What if it's a piece of shrapnel? Go show me the labeling for the shrapnel. There is none. Yes, so what? In the US, this conversation would be easy. I would turn to the radiologist in the audience and I'd say, well, who's legally responsible for anything that happens to your patient anyway? You are, right? Okay, so define what you would accept as the label. I'm sorry, what? Define the label for this implant. You want to call it a foreign body, call it a foreign body. Manny, what are you talking about? How am I going to, it's a piece of shrapnel. Okay, wherever that piece of shrapnel is, Manny, what magnetic field would you accept that you could expose it to before you were worried that it would hurt him? Plug in the number. And you say, what are you talking? 0. Fine. Why are you staring at me? Plug in 0. Do you understand? Plug in anything you want. It's like you're the doctor or something. Do what you want. You want to plug in 0. Plug in, I don't accept, if it's exposed to a magnetic field, I don't want it, I want to know. Fine, you can plug in any number you want. As you gain experience, you will be plugging in numbers you're comfortable with, like anything else in life. What dB dx would you tolerate? I don't even know what you're talking about. I don't even know what the numbers mean. Plug in 0. Plug in anything. What radio frequency exposure levels for B1 would you tolerate before you want this app to tell you, hey, you're irradiating this thing? If it's in the ankle and it's going to be exposed to less than 1% of the energy going on in this guy's pituitary, maybe you don't want to be warned about it. Maybe you'll say, I'm only going to care about this thing if it's going to be exposed to 5% of the energy going on inside the center, like mom standing at the front of the machine. How about that? Do you understand what I'm saying? You can accept predefined, because that's how this was labeled, or you can change them, or you can define your own for any device you want to create. You have an implant, which means it's not only a physical structure, but a labeled structure. And then you have a third room of the 3 rooms of this app is the operating room. I started out in surgery, and then I went into medicine, then I went into radiology. Ask me next year what I'll be doing, I have no idea. What happens in the operating room? In the operating room, the person running the app takes the patient they've already defined and the implant they've already defined or chosen and surgically implants into that patient that implant in the same location and orientation as it is in the patient you're about to scan. So if you have a patient with shrapnel in their left elbow, you go into the operating room, you bring in the patient this avatar is modeling your patient of a certain gender, height, and weight. You take that avatar, once you've defined it, you go into the OR with them, you take the shrapnel, and you physically implant it. I'll show you. You just put it into that patient's, left shoulder? Put it into the left shoulder. Wait, that's an elbow. Okay, that's the shoulder. I'm a doctor, I know these things. So you put it into the left shoulder, or whatever. You have a pacemaker, then you put it in the heart, whatever. Got it? Now you're just about done. Because now you go into the one room we're all comfortable with. It's called the MR room. And in this last room, in the MR room, there are a few things you have to do. What do I expect my technologist to know? What do I expect from the radiographers in this group? What magnet do you want to use? If it's one of the ones we've modeled so far, call it up. And I mean model, by name. What coil do you plan on using? Call it up if it's being modeled. What position? Is it head first, feet first, supine, prone? Define it. Then you have to center the patient. Now that you've got the magnet in front of you, now that you have the patient in front of you with the implant in that patient, now that you've decided I want to put him in head first, prone, supine, whatever, now position them, right? What are you centering on? And once you center, the second you hit that button, center, the report can be generated immediately. And everything you need to know from then on is already taken care of. For teaching purposes, I'll show you what happens as you advance the patient into scanning. But technically, you're done. At that point in the future, what I expect you to be doing is just press the report button, send. And I will get a multi-page report of that patient and every energy they'll be exposed to of that implant in that patient, in this magnet, positioned the way you asked me to position them, centered the way you asked me to center them, advancing them into the scan the way you expect me to. Exactly what fields will they traverse? What fields will they be exposed to for all of these different flashlights? It's just math. Why would you expect me to have to do that? If it's just math, there's no reason to ask either the radiologist or the radiographer to have to do it, right? Automate it. Everybody else in the world is automating everything. Why can't we automate it? So let's go through a few examples together. And please do not expect this to be anything other than an attempt to give you an idea, conceptually, first pass of what it is that the app is accomplishing for us. But whether you use the app or not, nobody cares. Somebody said it so beautifully in the break. What do we care about? Process. Think of what the app has to know in order to generate a report of what will be the exposures. That's what I have to know before I can make a decision as to the risks of this study on this patient, right? Process. Think about process as we go through the app. Under the guise of teaching you the app, let's see if we can review in much, much, much greater detail some of the things we've been talking about until now and where these actual fields really are. You remember that I showed you the red tube in which we had the blue gradient coils, in which I put the green RF coils, in which we slit another tube, in which a patient with a star at L4 showed up. And I said, this is idealized, because it's not that homogeneous. Do you remember that? Let's go through some that's a little bit less idealized. And I apologize for the display. This is the best we can get for the purposes. The first thing is you choose a patient. We've already created a patient, but just to give you an idea what I mean by that, we created Ploni Almoni, date of birth March 26, 1992, male, 5'11", and if you want, you can change it to centimeters, et cetera, kilograms, whatever, 154. This is a 70-kilogram patient. And now this means that the app will take the data you've given for gender, height, weight, and it now is created three-dimensionally already in the program. It already knows what that patient's generic approximate build and structure looks like. But now you can find, if you want to, you can fine-tune it. Let's just call it up so you can see what I mean. So this is that patient. A patient of that height, that weight, and what have you. This is a three-dimensional data set, so you can do whatever you want with the patient. It's a three-dimensional data set. But if you say, I change my mind, I'd like this patient to be a lot heavier. Fine. So now the dimensions will change, but it's now, until you change it back, this is gender, height, weight, gender, height, weight, gender, height, weight. That's all you need to know to make the calculations that I need as to what the exposures of the implant will be, remember? I don't need to know their age. I don't need to know skin color, gender, height, weight. If it's female, one of these controls will be pregnancy. It'll allow you to change the different months of pregnancy based on body habitus. It also is smart enough and intelligent enough to use use American patient databases from millions of patients. And as you increase weight, the deposition of that weight, the body fat, the distribution for males and females, as you know, is not the same. It's intelligent enough as you gain weight generically for the female. It will add it in different locations than it does if it gains weight for the male and vice versa. And you can have fine tune and control gluteus size. You can make the guy a bodybuilder, breast size, beer belly, etc. I mean, literally, it sounds cute, but it's exactly how males differ from females and how they distribute. So each gender will have its own distribution. So once you've decided, and you want this guy to be muscular, you want him to be a little weakling, whatever once you've decided, don't spend time. It's so far beyond what we need to calculate what we need. Ballpark, gender, height, weight. Once you've got your patient, and you've made this guy, he's the active patient, we have implants room where there's different implants that you can create or choose or define. There's an operating room. In the operating room, this is the only room in the app in which the patient is going to be naked. They must be. Think about it, it's like my OR, right? When I go in the OR, are you going to be wearing a bikini on me? I'm doing a mastectomy, a breast implant. I may have to do a penile implant. I need access to my patient. You know what this is like, getting this through Apple? Ladies and gentlemen, we're adding children, pediatric modeling in the future. Do you understand what this is? It's not a joke. This is a massive accomplishment with Apple, who is pushing this like crazy because it's the direction they want to see healthcare going, and you'll hear about that later. So conceptually, this is the only room in which the patient is naked and completely accessible. And this patient, in this room, anything, without going into too much detail, anything that you want, there's all different systems. There's integument, there's visual, the skeletal, nervous system, circulatory, whatever, everything here, any part that you wish can be displayed in any of three different ways. Invisible, visible, or translucent. So you can take the skeletal system and pick whatever part of it you want to create visible, invisible. We don't need to go into that detail. Right now, let's make everything invisible except for the skeleton and the circulatory system. We'll make those translucent. So now there is a pacemaker I've implanted into this guy's heart, and I think I gave him, yes, and there's also a artificial knee. Can you guys see it? I don't know if it's showing up. If not, I apologize. It's not as nice as here, but it's going to have to do. So this is that patient. I've already taken the time of implanting everything. This patient, as is now defined. It is the avatar of the patient in front of me I'm about to place in, or much more realistically, tomorrow morning at 11 o'clock. This patient of this gender, height, weight will be showing up. They have a left knee implant and they have a pacemaker left-sided by Medtronic Revo. It's all placed in beforehand. The patient is defined, and we finally go into the MR scan room. In the MR scan room, this is the most, let's just say, busy. But this is where we spend our time, so this is home for us. We've already chosen, in this case, it is a GE 753 Tesla, 750W. So now we're using a GE 753 Tesla, 3 Tesla. Everybody see this? Again, it's a three-dimensional data set, so everything is modeled. That means that this is the exact, and I mean to the millimeter dimensions of that make and that model of that system. But it also includes, let's bring the guy back out. It also includes the content, which means that technically everything, all the aspects of that device are there as well. The gradient coils are present inside. The RF transmitting coil is there inside. The magnet coil is there. To make it easier to see, let's do the following. Let's just make that part of it entirely. You can explode it and what have you, but let's just make that part invisible. So that way you'll be able to see what's going on inside the scanner. So the first thing we want to do is position this patient. Turn the laser on, advance the patient. Let's say you're going to do nipple line. You hit set, and then you hit move to the ISO center. So this patient is now being moved into the ISO center. This patient is now prepared for the scan. You chose, I forgot to mention, we already say head first, feet first, supine, whatever. You chose what you wanted to choose. You have your patient, you have the centering, you have the positioning, you have the implant. Top left, you can't even see, there's a little green blob up there. It says report. Right now, all I have to do is press that button, and it'll issue a multi-page report of exactly what energies will be experienced by this device. We'll get to that last. But right now, where are the energies? I made part of the machine invisible so you can see them. So let's turn on the B0 field. The legend is on top, and you can see that horizontal rainbow color. That means the different fields from 0 to 3.5 Tesla are shown, and it's color-coded, which means that these are the energies associated with this MR scanner and how they're spatially distributed. And notice the first thing of interest to you is that this is a 3 Tesla scanner. Just look at the side of the machine, 3.0 Tesla. That's what you paid for. So the first thing to notice is that what is the color of 3 Tesla? Seems to me, 3 Tesla seems to me would be right there where it says 3 Tesla. And that's like a, I don't know, purplish. And 3.47, that's like a white. Does everybody notice that this is all 3 Tesla, right? What's that? So the first thing to notice is that they've lied to us all these years, and nobody cares. You need to understand what he's getting at. Your 3 Tesla scanner contains areas that are 3.5 Tesla, that your patient can reach, that your implants can reach. Now, the first thing you might say to the uninitiated, well, holy frigging cow! You may choose different words. This is only approved to 3. Are you telling me I can never put him into a 3 Tesla scanner because he may be exposed? So I'm trying to get you to understand the amounts of leeway that are built into our safety. The FDA, of course, and all the other regulatory agencies know this. We're the only ones that aren't aware of this. Yes, they know that there are areas that are going to be mildly to moderately higher than what it's labeled for. Okay, that's part of the equation. When they label it to be 3 Tesla, what they really mean is up to a 3 Tesla scanner, not field. Because they recognize that one of the first things to learn is that the fields are not necessarily what you think they are. Secondly, the static field is not greatest in the center. It's actually greatest out there towards the periphery. for all of these systems. I'll show you. And it is different for every system. This is the B0 magnetic field. So let me ask you a question, seriously, before we get started. I'm going to hit the dBdx button. Can you please paint it for me before I press it? Come, talk to me. What do you expect the picture? I'm going to press magnetic spatial gradient. Where do you expect it to be reddest and whitest? Where do you expect it to be dark blue, weakest? Talk to me.
dBdz.
Where would yes, this would be a dBdz. What do you expect it to look like?
Into the board.
You should be ashamed of yourself that you're letting your physicist answer the question for you. Take it away. He's going to help you this time, not the next few.
Okay, the edges of the bore.
Edges of the bore will be
The entrance and exits to the bore on either side.
will be hot.
Yeah.
And where will it be weakest?
Center.
And where will it be weakest? This is what it's like for B0. This is what it looks like for dBdx. This is what it looks like for dBdx. Let's bring this guy in and show it to you this way as well. Can you see it? Even looking down the bore, notice how much weaker it is at the center than it is at the periphery. Does everyone understand that? And exactly as he said, the center, there's almost no dBdx because in the center is where it's homogeneous. So the magnetic space, this is the exact same information I showed you before. Remember those field plots? It's just a little bit more colorful. Actually, it's 5 cubic millimeter spatial resolution, so it is higher detail, but it's the same information. It comes from the same, all the information that you're seeing, every single bit of it, the origin is not me. It's all coming from the manufacturers of these machines. This is the dBdx. Where's, don't you dare. I'm going to hit gradient dBdt. Remember the gradients that turn on and off, antero-posterior, super-inferior, left to right? Anybody tell me what you expect those to look like? Come on, talk to me. Everybody go like this and tell me if you feel anything. Yeah, say it out loud. Let me hear. It'll be lowest right in the middle. And as you go out, and where will the edges be? How the heck should I know, Manny? That depends on the magnet's configuration. Where are the gradient coils for that specific magnet? Do you understand? Why should I have to memorize that stuff? It's just math. This is your dBdt. Let's bring this guy back in again to show you what it looks like head-on as well. This is the left, right, front, back, super inferior gradient. Let's go back in case you didn't catch it. This is dBdx. This is B0. This is the gradients. These are imaging. These are the energies that result potentially in neuromuscular excitation, remember? So if you're centered, let's go back and pull this sucker back out. Turn the laser on. Let's do canthomeatoline. Center. We're about to do is pit. Advance. You see where he's centered now, right? Remember what this patient has? See the pacemaker? What color is the pacemaker? We'll get back to that in a minute. Let's put his skeleton back on. He feels naked without it. So when you center this guy for the pituitary, you max out dBdt right over his pacing system. Do you understand? What will RF look like? What will the RF energies look like? I don't know. What coil are you using? What's the dimensions of that coil? This is RF for that same magnet. This is the RF for that same magnet. Let's bring that plane back in here so you can see it from the side. And again, the data is from the manufacturers of the device. Where is the greatest by far? Approximately 10,000 greater than the center. Approximately 10,000 times greater than what's happening in the center. Where's the greatest energy? This is a body coil. Where's the greatest energy? Talk to me. And the edge of the bore. That's where the burns occur. We call those proximity burns. We didn't cover those today. Did you ever read where it tells you keep your patient's tissues from touching the outer, don't touch the bore, keep them 5 millimeters, some say a 1/4 inch, some say a centimeter from the outer bore, from the edge of the bore. Now you know why. So conceptually what this will do, for teaching purposes only, is just trying to show you the spatial distributions. Remember we talked about force product? Force product is for metal that is not fully magnetized. Where is the greatest attraction into the bore? So this is the force product plot. Another way to do that, I kind of like this even better. I just built in this little bugger. That's the greatest possible attractive location in the magnet for this machine. And you can sort of see, like, if you'd be leaning, let's put that back. Can you see where that would be? Oops. While you're on that, conceptually, another thing you can do is, I just realized I might as well just show that to you. I can turn on a field plot. This is the 1000 Gauss line. If you were to erect a wall, you know how you put, some people like to put marker, I think in UK you guys do mark off the 5 Gauss line. In the US we don't do that yet, certainly not regulated. So you can pick whatever field plot, oh boy, that's really not showing, is it? But you can pick whatever field you'd like and just say map it out and tell me where in space that field is. And as you change the field, it'll show you where that is, either as a wall or as a 3D bubble plot showing you the distribution of that exact Gauss line. Or I shouldn't say Gauss line, because by definition we're not dealing with lines, we're dealing with 3-dimensional objects. It's just that we're not used to thinking of them that way. Now for the first time you'll have the ability to just visualize 3-dimensionally where is that Gauss line, which is really a Gauss wall, as you have a certain distance from that magnet. So from a teaching point of view, it's meant to help illustrate for you what is going on where. But more importantly, there's something here that I've not done, and let's do that together. I'm going to pull him back out artificially, but now I'm going to turn on one more function. And as we advance him to scan, I want you to look at something else is going on. Look towards the legs of this patient. Let's put him into transparent mode. We'll make him partially translucent. And as he's advanced to scan, we turned on the B0 field. See, he has a green pacemaker and it's dropping green balls. It turned yellow and it turned red. I'm not sure you can see that. Let me blow it up a bit. Can you see that? The pacemaker and the balls that it drops, I think of them as breadcrumbs. The pacemaker is labeled, isn't it? And so this is just giving you a 3D spatial distribution. At this location in space, it's green. That means that you're nowhere near the threshold for which it's been labeled to be safely scannable. Yellow means you're approaching a threshold. Red, well, red means you've already passed it. So at these positions in space, wherever it was out there was not an issue, yellow was approaching, and in no time at all, in no space at all, in this example, that pacemaker on that MR scanner exceeded its safety for the, what energy are we looking at, B0? It had exceeded it right there. Does everyone understand what it's trying to show? And it's leaving a red, yellow, green, I'm so sorry, red, amber, green. I never got used to that. I'm the one you'll read about in the paper that got killed taking a step off because I keep looking to my left and there's no cars coming. It's going to leave you a three-dimensional plot as to exactly where did you approach or exceed a published threshold. This is B0. Look carefully at the balls. Nothing up my sleeve. This is dBdx. What the heck is going on here? I see green, 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 green. We'll get to the other green is the knee implant. Green, 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 yellow, 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 green, green, green. Can you see that? Seriously, guys, you all right with that? Do you see what I'm referring to? It's green, it's yellow, and then it goes back to green. And the pacer is green. So what's going on? For this energy, which is now being explained as dBdx, the maximum dBdx that this thing could tolerate was approached where it turned yellow. Notice that was greatest at the entrances to the bore. It never exceeded, and then as you got towards the center, oh my God, that's right, it goes down to 0 in the center. It became green again in the center. Because it's constantly doing what I don't want to ever have to do again. Comparing the number that it's labeled for to the three-dimensional space around and in that magnet for each of these energies. This is for dB/dt, and this is for RF. If you decide to change the scanner and go to a 1.5 Tesla, everything else will be the same, but the calculations are instantly performed at 1.5. What before was for static field, remember we had green, a little bit of yellow, and immediately red? It never reached red now. It's just yellow the whole way through. You may approach, but it never, at 1.5 Tesla, it never exceeded the published safety threshold for that pacemaker, which I guess was at 1.5. Does everyone understand what it's trying to do? Don't get bogged down in the details. And then the most important aspect conceptually, I hit report. You choose what you want in the report, and you can, of course, choose to take pictures of the screen or what have you. But at some level, you just hit the report button, and that's it. It will generate a date and time-stamped report of who's operating the app, who's the patient if you choose to do so, because you have to keep patient privacy. Protected health information has to be guarded at all times, so this can be done with or without patient information. You never have to plug any of that in if you don't want to. And it presents all the data in 4 different ways. It will present the data in a table, and it will tell you for each of the 4 energies that we talked about, B0 static field, the static magnetic field gradient, RF B1, dB/dt, gradient imaging. For each of those 4, it will tell you the report. It'll also give you a force product, the greatest attraction. And it'll tell you what is the labeling for that device. You'll notice that there's 2 implants in this patient. So when it's finished with this one, it'll give you the same report for the next one. It'll tell you what was the labeling, what did it experience at the position it would be scanned in, what was the minimum traverse value, and what was the maximum traverse value. Anything red means it exceeds a user-defined or published threshold. If it's not yellow or not red, that means it was within threshold. And it'll present that data 4 ways. It'll present it by a table like in front of you now. It'll present it as a graph for each of the energies, B0, dBdx, dBdt, and RF. It'll present it as 3D images of your whatever scanner you picked is going to show up in this page. And it'll show it to you from the front, from the side, and from the top. And it will show you by color coding for each of these energies, B0, dBdx, force product, there's another one down here, dBdt, and RF. It will show you for each of the energies, if there's nothing there, then there's nothing exceeded or approached. If it's yellow, that means you're getting close. If it's red, that means in those areas it would exceed, three-dimensionally, in those areas it would exceed what it's labeled for. And finally, it'll also present the same thing, my favorite, the executive summary. It'll give it to you in English. It'll do that for whatever implant, or if you have more than one, for every implant that you have in there, it'll give you its reports. And if you have any images that you wanted to screen capture, you can do that. And it'll save those as well. And then you can press a button and send it to your radiologist, medical record. It's a PDF, for God's sakes. You can do whatever you want with it at that point. And then I can be 3 buildings away. You send it to me. I look at it. Being a radiologist, I see no red. I say, go ahead and scan. Or maybe we have a discussion depending on what I see. And then the patient can come in tomorrow at 11 o'clock and you can proceed as you've already analyzed. Summary. Please forgive me, in the course, there's a massive amount we focus on the actual executing and how to run the app. That's not the purpose this time. So please forgive me. Stop thinking about the app. That's not the purpose of today. The purpose today is process. I'm going to have 4 different energies that I need to be aware of. I need to be aware of the existence and spatial distribution of a static field, of a magnetic static spatial gradient, of B1 radio frequency transmitted energies, and imaging gradients dB/dt. Not only that they exist, but where in space am I depositing them? Because they're all different and they're all unique. And after I do all of that, I get a 1.5 millimeter thick coronal slice of his pit, and that doesn't interest me. From a safety point of view, only reason I needed to know that it was a pit is how is his body being positioned and where will I center? That's the only thing that makes a difference from a safety point of view now. How is his body being positioned and where will I center? Of course, the actual imaging sequence will also determine maximum RF power. We'll get to that another trip. So what do I need to know? Forget the app. To decide, can I safely scan this patient? What do I need to know? Gender, height, weight, magnet, which hardware, what field strength, what coils are transmitting, how did you position, and where did you center? I'm going to take all of that and I'm going to apply it to your knowledge of the implant or implants that this patient has on or in them, and I'm going to finally make a safety risk assessment. One thing this is never, ever doing for us. You notice how many times I told you have never met anybody more anal compulsive than I am. You have no idea how carefully I'm choosing these words. What word have I never, ever, ever used today in describing whether I'm going to scan this patient? I've never used the word benefit. But Manny, you have to do a risk-benefit analysis, a benefit-risk ratio. Nothing in any of these apps ever, 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 ever is attempting to assess potential benefit. Should I do a myelogram instead? Is a CTA going to be just as good? That's not what this is telling me. Potential options. Why? It's a cord compression. Or no, they just have a headache. It's not assessing any of the potential benefit to the patient. Alternative, none of that. The only thing it's attempting to analyze and even pseudo start to quantify is risk. I cannot do a benefit risk assessment if I don't know what the risks are. Your natural skills as radiographers, we've already discussed. My hopefully natural skills as the radiologist in the equation talking with you when you bring that patient to me is to understand the potential benefit to the patient, potential alternate tests, what options there may be. But I might, in the US, I would need help from you in helping me understand and assess the risk. And so now you understand at the end why what I said at the beginning holds true. This is actually designed to be used by a radiographer, but make no pretenses or mistakes. In the US, radiographers do not have the abilities, the controls, the legal authority that radiographers have here. There's exquisitely clear division of power and authority and legal liability and responsibility in the States. And so in the US, you will bring that information to the radiologist, and then they have a decision to make. So you'll educate me on the risks. I will hopefully bring to the table an understanding of the potential benefits and options. And between all those, we can finally, for the first time, make a semi-knowledgeable benefit-risk assessment. I hate that we call it risk-benefit. I always like to think of the potential benefit first. It's a benefit-risk ratio. Should I do this or should I do something else? Or should I can the study entirely? And maybe go to a CT or something else instead, or whatever. So, in review, The only thing that this specific app, this app is called MagnetVision, the only thing it's trying to do is to help us quantify risk. It does nothing for potential benefit or options. On attempts to quantify the risk, I am so extremely heavily dependent upon the radiographer, because I will need you to define the magnet you want me to use, which coil is transmitting in that magnet if you have a choice. How are you positioning that patient for the study that Manny asked me to execute? And where did you center that patient for that study that you positioned in that fashion for that study? Got it? I need all of that to come from you. In the US, I need you to tell me what implant they have on or in them and how is it labeled. That's all happening before I even get to the room. All that you're bringing to the table. But if I have those pieces of information, if Manny can quantify the risks or pseudo-quantify at that point, I can start to assess, is it being exposed to any serious transmitted energies or is it not? Then the app can do it for us too, and can do it in a more quantified fashion than Manny ever could. So if you only think of what information do you have to plug into the app for the app to simulate, now you know what information you'll have to bring to me. Whether I have an app or not means nothing. What information am I going to need to know before I can answer the neurosurgeon's question, is it safe to scan my patient? And why I might say yes for this study and no for that study, for the same patient in the same MR scanner with the same hardware for a different part of the same body. Show of hands, how many of you regret having spent your Monday here so far? Are there any questions so far? Yes, ma'am. This patient, would I scan them? On what? Oh, okay, so listen to what you just asked me. I don't know the specifics, we'll get to in a moment. She'll define for me. So she said, so some patient right there in front of you, Manny, so would you scan them? What's my answer going to be? Every one of you now knows enough to know what I'm going to answer her. It depends. Why? Answer her question. You just told me it's math. Answer her question. We haven't discussed benefit, have we? When you ask me the question, would you scan ... by definition, that's a benefit risk question, isn't it? And again, we don't discuss benefit by this app. So now, when you do this 24-hour course, oh man, you have a 26-year-old patient with multiple sclerosis, or at least they think it's multiple sclerosis, and she comes in here and they think that she may have either cord compression or she has a lesion that's on the left side and the left approximately L3 and below. We'll give you everything. Then let's see how you do, big shot. Now let's see you answer the question, Manny, because now we're going to put an implant in that patient with a specific application, with a specific diagnosis, and then we'll show how we reason. Then together we work through reasoning all the way to that point of answering your question, would you or would you not accept that patient for scanning? The title of that, it's 3.5 hours. The title of those 3.5 hours is, would you scan this patient? The title of the lecture, I can show it to you right now. The title slide, would you scan, the name of the next 3.5 hours is, would you scan this patient? But I can't answer that question here because at best, once you tell me what specific implant or what specific magnet, I use 2 different magnets and different coils, when you narrow down, at best, I can begin to pseudo-quantify a level of risk, but I haven't given you an answer yet as to what the potential benefit is. And if they're coming in for a cord compression and the potential risk is to this tissue or that tissue and it's this much, not that, I might say yes, I might say no. This app will never, none of my apps will ever tell you, scan or don't scan. I was raised as a surgeon, and I was raised from day one, old enough from the first day you walk in. One of the first things they always said is, don't you ever, ever, ever tell me how to take care of my patient. It's ingrained in your blood, every blood cell screams out, don't you ever tell me how to care for my patients. That's every physician in the world should be thinking the exact same way. Teach me, guide me, absolutely. At the end of the day, it's my patient. It's my patient. And I may not even care what that doctor would do. At the end, I'm responsible for what I did to her. And so each of us may come to different, and that's what we show in the course. will have the same exact clinical situation with a specific scenario on a specific patient with specific potential benefits. Some may say yes and some may say no. And that's 100% wonderful. That's why it's called the art and science of medicine, isn't it? All of you know some radiologists that are much more aggressive and some are, okay, maybe not radiologists. All of you know some physicians that are aggressive and some that are not aggressive. All of you know that there are different personalities in MR, in radiology. Some physicians are really gung-ho, yes, we got to do this, we can get this done. Others may be, no, let's relax, I'm not so sure. Companies have different personalities. Don't ever tell me how to practice medicine. Just because Manny said he would do it, half of you could be sitting there saying, oh, he's out of his mind, I would never do that. It's 100% right. That's absolutely fine, and vice versa, because I'm responsible for the care I provide to my patient. And you, young lady, are responsible for either, number one, carrying out my orders, now listen to number two, or being prepared to give me a darn good reason why you think you're not. That's part of the course too, medical legal. In the US, you say no to me, whether you liked it or not, you think you were doing it for safety, you've just exposed yourself to a legal consequence that wasn't there a moment ago. And that's part of what we teach as well. Because as you know, you may think, you know what, I'm not going to have any part of this. There's no way I'm doing that study. I've had almost a half a dozen people come to me in different courses in my life where they've said to me, Dr. Kanal, what do you do? And they say to you, scan this patient or lose your job. Maybe it's just US. Almost a half a dozen have said that to me. Direct, personal, in between lectures, Dr. Kanal, what would you do? And I answer them always the same. I have enough trouble knowing how to live my life, what I consider the proper way. Please don't look to me for philosophy lessons. I don't know what I would do. I can tell you what the science can support. And then, in the US, I can do a pretty good job of telling you what the consequences of your decisions might be. But I can't tell you what you should do. That's not my job. Don't ever, ever tell me how to practice medicine. And I'll never tell you how to practice medicine. The same exact conclusion from this app can cause him to say absolutely and me to say no way, and they're both 100%, in my opinion, they're both 100% acceptable. So please, we'll list a bunch of questions and we'll read through and try to go through them together, but then when you have questions, please, please, please yell them at me as well. I'll see you when you come back after the break. Thank you very much.